Okay, everyone. So, new chapter. I am assuming you guys are all on top of chapter 4 and 5 at this point. And as I said, I'll go back probably to some other examples about rigid body problems, but we're going to start a new way of solving problems, which is a different approach with respect to the Newtonian approach, which is the one that we followed so far. So this is analytical dynamics, and in particular, we're going to end up deriving and using, not today, but these will be our tools, Lagrange's equations. Okay, so this lecture is really like the very first lecture when we randomly defined a few things. We introduced concepts that will lead to finding those equations next time. And so I'm going to start with a simple example, which is the usual pendulum, right? And we're going to do it for now. Probably I won't be pushing it more than these. We'll see for a single particle. We'll see if we can expand. But let's start with one particle. So pendulum, this is just a rod with no mass. The mass is concentrated at the end. We have a single particle here. There is gravity, of course. Otherwise, it doesn't make any sense. Can't call it a pendulum. So, and this is an inertial reference frame. The ground is an inertial reference frame. What have we done so far? Well, we defined reference frames, and then with the ground, we have defined probably its basis, Ex, Ey, for example, and then here we said I'm going to define another coordinate system which has Er along the pendulum direction, OP, and then some E theta, which is normal to that, and you can always think about it as a Z direction if you need it. So, and all I've done is giving you these variables here. I will give you this theta angle, right? But why am I doing this? Why am I choosing theta? Because we don't ask ourselves this question. It kind of makes sense, but why? Everything we've done so far, starting from a single particle, then we went to systems of particles, and then rigid bodies, we have decided to define coordinates, X, Y, Z, angles. That's pretty much what we've done. In a certain way that makes sense, right? But why does this make sense?
Radiation from equilibrium?
I am kinematically thinking about this problem kinematically for now. So no equilibrium, no forces. I forget about gravity. Why, if I look at this problem, where this is a fixed length of force, L, OP, why, when I draw that theta angle, no one complains and says, yeah, that's cool, we use that? Yes?
Because it would allow you to see the motion of particles function of a single variable.
Okay, we're getting there. How many degrees of freedom does this problem have? One, okay. So I do know that I need one coordinate to represent the configuration of this system. This is a stupid system. It's just a particle that can only go around a circle, and that should give you another hint. This particle can only go around point O at a fixed radius L. And so it kind of comes naturally to pick an angle. But I don't have to do that. I can, if I feel like doing it, I could pick X and Y, right? Ex, Ey. That's perfectly fine. So, and let's do it both ways, just for fun. Let's attack kinematics both ways. So if I stick with that single variable, I know that r, the position of the particle, is what? L, Er, right? And I also know that the velocity, and from now on, in Lagrange's equation, it's a given that we're going to take derivatives with respect to inertial frames. So I may start dropping these G or N, because we're going to work in inertial frames, but let's try to keep it there for now. And G is inertial, just to make sure. It's an inertial reference frame. So what is v of g? Let me not define the angular velocity. I know the angular velocity is theta dot e z, blah, blah, blah. It will be L theta dot e theta, right? Is that right? Okay. But since I can do it because I feel like doing it, it's my prerogative. I want to do it the other way. I also want to say that R is x ex plus y ey. I can do this. And then with this type of parameterization, I get x dot. This is the velocity. I'm sorry. V g is x dot ex plus y dot ey. This is perfectly fine. I can do that. I can make my life as complicated as I want. There's no one stopping me from doing so. The way you parameterize a problem, it's your issue. Physically, this is the same system. If you choose theta x, y, gravity is not going to change. The mass of this is not going to change. You're just representing in a different way. So what is the difference between those two now? Why? I see one variable here, right? I see two here. But it's the same problem. And I said I have 1 degree of freedom. So probably I need one variable. But these equations, they all make sense. These vectors, they all make sense. What's the difference?
Now we have two equations, two differential equations.
Yeah, but I know that I don't need two differential equations, right? So one is probably redundant. What am I missing here?
So there is a constraint for the second.
There is a constraint here, right? There is a constraint here, and what is that constraint?
X squared plus x squared.
X squared plus y squared is L squared. So this is your constraint. Okay, cool. So, and what is the constraint in the first one?
Theta has to be between
No,
0 and 1.
it can go around as much as you want, several times. I can kick that mass and it keeps going. L is constant. So I'm just trying to underline here is that the difference between approaching the problem in these two ways is that here, I kind of skip that step. A particle in a plane has needs in general two parameters to be located somewhere, right? With my first approach, with the first one, what I did is I picked two variables. I picked theta and L, but these happen to be constant. So in all the problems that we faced where they were looking like this, where I just gave you an angle or maybe two, I just implicitly said there is a constraint. I don't even write it down. But it's the same. I start from two variables, but then I go down to one because this is not changing. While here, if I give you this, I start from two variables, and then I have to write a constraint, which is pretty ugly because it's non-linear in those two variables. So what I'm trying to get at is that we look at a problem, we look at the geometry of the problem, and we define these variables that kind of make sense, but that kind of makes sense means that we are taking into account the constraints of the problem. By picking theta, I am implicitly saying there is a second variable that is constant, because I'm not caring about that one. Because if I take L dot, that's 0, right? Okay. So these variables we pick are consistent with the constraints. That's what we've done so far. We picked variables that make sense when you consider the constraints. Okay, that's the first observation. Now, what do we want to do? Yeah, we don't need this. If I stick with the first representation here, if R is a function of theta, because this is what I'm telling you, that r is a function of theta, right? If I use that parameter only, r is a function of theta. R dot, and the same, from now on I'm going to use the dot, meaning that this is the derivative in g of something, in this case of r. So let me use the dot from now on. We're working in an inertial reference frame with Lagrange's equations when we'll get there. So if I tell you that a position of a particle, remember we're working with a single particle for now, it's a function of a parameter. In this case, it's an angle. How would you compute r dot? It's the partial of r with respect to theta, theta dot, right? Cool, okay. But I know that this is also equal to what? L theta dot E theta. And so this is telling me what? dr in d theta is equal to L E theta. So other than a constant, it's this direction here, E theta. And I hope it's clear to everybody that the partial of a vector with respect to a scalar, it's a vector. Of course, that's what I'm saying there, because it's equal to a vector, but it makes sense. That r is changing as you change the angle theta. Remember, r goes from O to P. It's this vector. So as I change theta, I have a new r. And so the variation of r with respect to theta is the delta vector, the change in r. So it is a vector. OK. Let's change the problem a little bit. It's the same pendulum, but now, and we have seen this already, the attachment point O is moving with a known law of time, y of t. This is given. OK? All right. So for this new problem now, so this is old pendulum, if you want. Pendulum. And then we have the new one, where the attachment point is moving. What is the position of P in this case? How do you write that position? Remember, I have to write r with respect to the position of P, which is r, with respect to an inertially fixed point, because I'm going to take all derivatives with respect to an inertially fixed point. So O is not inertially fixed anymore. It will be this other point here, O prime, if you want, that is inertially fixed. So this can be picked as the origin for the coordinate system, which is fixed to the ground. So r is now something else. Is this y of t, and of course, let me call it x of t, just to be consistent with my axis. X of t, whatever that is, big Ex, plus, same, right? L ER, that's it. And then my velocity, so I told you I'm going to start calling this r dot, is going to be x dot of t Ex plus this is going back to basic stuff that we've seen in the first days. It's the same, right? OK. So the velocity now is different, of course. The attachment point is moving with some given law, which I don't need to tell you what it is. I want to compute the same thing, though. What is this? What do you think that is? Does x of t depend on time? I'm sorry, yeah, it depends on time, but does it depend on the angle? Doesn't depend on the angle, right? So if I take the partial of this first portion with respect to the angle, it's 0, and then I have the partial of this, or I have L d E r in d theta. And what is that? That's a good question, huh? Going back to very basic stuff. ER is a unit vector. Magnitude 1. What is the rate of change with respect to some? Now my independent variable, think of theta as, is not time, but it's another variable. It's the independent variable here. Theta would be a solution of time if you integrate your final differential equation. So where do you expect the rate of change of a unit vector to be pointing? It's this, right? It's the same. You get the same thing. And that's very interesting, because what is happening here is that this direction, when I have a small change in the variable theta of my problem, and let me just underline here that I still only need theta for this problem. This is still a 1 degree of freedom problem, because x of t is given to me. The attachment can do whatever it wants, even if this was moving on a circle and that law is given to me. I don't care. The only parameter that I need is theta, or just one parameter. So the direction that is given by dr in d theta is the same in both cases, even though their velocities are completely different. The velocity of p is different with respect to the ground if I have a fixed attachment point or a moving attachment point, of course. And so this leads to what is really the basis of analytical dynamics, which is we started looking at things freezing time. In other words, if I stop the passage of time, so I freeze my x of t to a given configuration here, and I allow the angle to change, what can this point do? If I freeze time, that becomes a simple pendulum, right? So P can only move along a circle which is centered at O, which means at a particular instant in time that I've frozen, I can only go along E theta, right? It can only be tangential here, motion. So what that direction is giving me is the motion that is allowed by the instantaneous constraint. Do you see that? This is my constraint. This color here that is moving on the guide is my constraint. I'm just telling you, in the other case I was telling you O is fixed. In this other case I'm telling you O is doing this. For example, going back and forth with a sinusoidal time law. I don't care. But that's still my constraint. It's a given. And so there is a similarity between the problem where this doesn't move or this moves, and that is that if I freeze time, in the first case it doesn't matter because O is not moving, but in this case it does, your motion, the motion of the particle, needs to be consistent with the instantaneous constraint. So these partials of the position with respect to the variable, in this case there is one variable, are giving you the directions in which the particle can move if you are freezing time, which means instantaneous constraints. What is the constraint right now, at this very instant? It's position O. It's not moving. But I allow the variable theta to move, my only coordinate that I need to represent the configuration of the system. I know this is confusing. But that's what that is telling me.
This is,
Go ahead.
This is no longer true if we move from kinematics to kinetics, is it?
Say it again, I'm sorry.
This dr by d theta
Mm-hmm.
is same for old pendulum and new pendulum we are saying in this scenario. But if we move from take kinetics into case, in that case this is not true. Is it?
I'm doing kinematics for now. This is all kinematics, first of all. Right?
If we move from kinematics to kinetics,
The kinetics will be right in the Lagrange equations, and we're going to use this concept of virtual displacement, which I need to introduce. But no, this is true. This is true for every problem. If you have, so let me generalize here. let's generalize this. Are we all, with this example, do we all agree that if I freeze time, what this particle can do is move along theta, and that partial of the position of the particle with respect to the only variable that I have in my problem is telling me what is the allowable motion compatible with the instantaneous constraint, right? So in general, let's generalize this, and hopefully this will answer your question, and we can go back to that. So hold on to that question. Okay, in general, in a problem, and again, we're doing particles here, we have, say, m degrees of freedom. In this case, it will be 1. So this is m. As in matter, n as in Nancy, variables to describe what we call the configuration of the system. In this case, that was 2. That is my initial number of variables that in general I would need for the particle in a plane. That would be 2. But then I have actually 1 degree of freedom because I also have, in general, p constraints. And the relationship here is the following. M, number of degrees of freedom, is n minus p, right? So if I start from the free motion of a particle in 3D space, that n is 3, then you start adding constraints, and that brings down your degrees of freedom, right? We prefer to parameterize the configuration of the system with the so-called generalized coordinates, which I'm going to call Q's, Q1 up to Q little n. And this is in general different from big N. Now there is a temptation to say, okay, this n should be equal to the number of degrees of freedom. It doesn't have to be. But this is in general. So in this case, my Q was the angle theta, right? I only had 1 Q. And so since I'm going to stick with a single particle, this is what I have. For a particle, we have that R is going to be a function of Q1, whatever that is, Q2, Q3 at the most, right? I don't need more than 3. That could be X, Y, Z. And so the velocity R dot is going to be dr d q1 q1 dot plus dr d q2 q2 dot plus dr d q3 q3 dot. If that doesn't depend on time. And we've just seen a problem where that actually depends on time, right? So there could be a time here. So you have dr in dt. So these things here, these partials, will be these are compatible with the instantaneous constraints. So this is in general. If you've chosen these Qs, I should have said this, these are also compatible with the constraints. Compatible with constraints. So if we go back to your example where the Q was only one of them, theta, it was obvious that direction was what the particle can do if I freeze time. Well, this is in general. If you have, for the particle, you can't have more than 3, of course. Doesn't make any sense. Otherwise, it would be overdetermined. These partials are giving you the motion that you can have being compatible with the instantaneous constraint, meaning that you're freezing time. So going back to your question, which was, if I go to kinetics, what does it change? I don't see why this should change. This is just kinematics.
No effects of PS like freely. We are not providing any. I was just thinking if the O point, it's moving and its frictionless bar and it can move. When it will go at left side, then the bar should also move to the left side.
Well, in my example, I was assigning the motion of xt. So whatever the particle is doing, the motion of xt is given. So it's either fixed, as in the regular pendulum, which means that you put a nail there, and there is a reaction such that it doesn't matter what you do with the mass. You can kick it as hard as you want, always will not change. Or there is some actuator that will impose a motion. It doesn't matter what the particle is doing. You can do that. So that's a constraint can be something that is fixed in an inertial reference frame or is moving with an assigned function of time. That's perfectly fine. But if someone tells you this point is moving with this function of time, you're not allowed to change it. It's a constraint. It's just not a time, not a fixed constraint. It's changing with time, but it's fine. But what we need to understand here is that these directions are what the particle can do when you take a picture of your system and you imagine that whatever these constraints are not moving, they're frozen. The only things that you can change are these, basically the variables that represent the configuration of your system. Does it make sense as a concept? So you can have, again, you can imagine many cases. You can have a circular guide and your particle, I think we've seen problems like this, is moving on a circle, but then this circle is translating with time. Well, the instantaneous constraint is this. You can only move tangentially to that circle if I freeze the circle. Then on top of that frozen motion, and this means that I have probably allowed this theta angle to change, right? But not time. Well, then in addition to that, there is all the translation of each point here. But I am not allowing passage of time at the moment. I'm only taking these partials with respect to the Qs. So if you want to generalize this concept of something moving even though time is not changing, we get to the definition of virtual displacement. A virtual displacement, remember, we're back to a particle here. Displacement is defined as compatible, again, with the instantaneous, let me not rewrite these constraints. This means no passage of time. And these were indicated with D delta r. It's summation 1 to 3 partial of r with respect to qi delta qi. So as you can see in this definition, there's no time. The only thing that is changing virtually is not really changing. I'm imagining that I'm freezing time, and I only allow these q's, again, your theta at the beginning, to change. Nothing else is changing. So there is a delta virtual displacement on the variables that parameterize my problem that corresponds to a delta displacement on the position, which can only occur in specific directions in 3D Euclidean space in this case, that need to respect the constraint. So again, imagine this. Want to imagine this in 3D? That's a sphere. Your particle is moving on a sphere, but the sphere can also do something else. Well, your instantaneous constraint is that you can be in a plane tangent to that sphere at that particular time only. That's what it is. Is this? I'm only giving you definitions here, and I wanted to lead to these definitions by just a simple example like the pendulum. Are there any questions on this? Before I do something else that will sound even more strange, probably. So the problem in general, you start, this is a particle, you start from, for the particle, what did we say, the n was 3, right? That's the number of variables you need to tell me where a particle is in 3D Euclidean space. But then you may have some constraints this can go, of course, from, well, it needs to be less than 3, otherwise it doesn't make any sense. If you give me 3 constraints on a particle, then it doesn't go anywhere. And then the number of degrees of freedom are n minus p, and usually correspond to the number of the q's that you pick. Right? But in that case, where the pendulum was moving, well, doesn't really apply. But anyways, the bottom line is you have constraints. They can change with time. In defining virtual displacement, you don't care about that change in time. You freeze time, and that's how you define dr, delta r, which is something that we're going to use. So, and we do this, we've done this every single time. We have defined, in all the problems that we solved so far, we have defined these q's. That's all we've done so far. You don't think about it that way, but that's what you do. You define q's that are consistent with the constraints. Before, when a couple of lectures ago, when I solved the problem for the gyroscope, or the top, I picked 3 angles, because I knew that there was going to be a good way to represent what was going on, orientation changes only. Picking x, y, z for the position of center of mass could have been another way, but could have been probably a painful way of doing it. And having more than 3, it would have been redundant. So you would have equations that you don't need. So in every problem that I've given you so far, we picked, for example, the pendulum, we picked theta just because I told you pick theta. And I started saying this is theta angle. But it's what you are doing there, it's important to grasp, is you are defining a generalized coordinate, theta, which is compatible with the constraint, right? And that's the definition of virtual displacement. So we'll use it. I know this stuff at the beginning seems a little strange, but when we'll derive Lagrange's equations, we'll see how powerful they are. They will allow us to write differential equations of motion projected along directions that they don't need to be orthonormal. If you think about what we've done so far in most of the problems, when we got to the point of finding the equations of motion, I would tell you equate these ma on the x direction to the forces that you see on the x-axis, the same for the y, the same for the z. We play with orthonormal directions. But we have actually solved problems like the gyroscope problem where the coordinates are not orthonormal. The 3 other angles are not orthonormal. So we've done it before, even though we didn't approach it with Lagrange's equations. But this is the formal way, as we'll derive it next time, to actually write differential equations of motion projected along directions that don't need to have any restriction among them. You can have an angle and direction. They don't need to be orthonormal. And it takes into account the constraints. So you actually forget about that step where you need to figure out, okay, how do I get rid of the reaction force? You just don't deal with that anymore. You don't deal with that anymore. So that they're extremely useful. They make your life easier. You can't find reactions, as we'll see, unless you're interested in finding them. You're fine, but if you do, then you can't use this. But that's for later discussion. So the other thing we know is this: for the particle, we know that Newton told us, until you prove me wrong, the force that is acting, the resultant of the forces that is acting on the particle is going to be equal to the mass that multiplies the acceleration of the particle in an inertial reference frame. So n must be inertial, otherwise Newton's laws don't apply. Now, so this particle is traveling on its trajectory, doing something, Pm. Remember when I defined my, what did I call these? Et, En, Eb? The intrinsic coordinate system. So what if I now sit myself on the particle? So I'm sitting on top of this particle, and so now I'm not in an inertial reference frame anymore. I am in a reference frame, and this is an abuse of terminology, that is centered, if you like, that has the particle as one of the points. So you can imagine that this coordinate system is fixed in that reference frame in which I'm sitting. So I'm traveling with the particle, right? What forces do I see? Or what acceleration do I see for the particle? You don't see anything, right? So if you are in that frame, this is what you get. Equals 0. Okay? Now this in your book, and by all those who do dynamics, is not Newton's second law. This is not just taking this and bringing it to the other side. This is called D'Alembert's principle. Why is this not Newton's law? Well, because I'm not in an inertial reference frame anymore. I am in whatever reference frame it is that has the particle fixed in it. I am sitting with the particle. So I know it looks like I brought that on the other side and I equal that to 0, but you are not, I am not in n here. So it is not Newton's law, because everything we said about Newton has to do with inertial reference frame. This is not an inertial reference frame. So these are the ingredients we need to use. The idea of virtual displacement, the fact that you can look at a problem and freeze time and define in which directions in space a particle can move, which are consistent with instantaneous constraints. That's something you need to grasp. And we'll use these to derive Lagrange's equations, which are another way to formulate problems, to find your differential equations of motion projected in directions that can be anything, but that automatically takes into account the constraints, because those Q's that we'll use are chosen to be consistent with the constraints. So we'll see the reaction forces will just go away. Yes?
If you're not in n anymore, why is there a superscript on the acceleration?
Well, I can always have a vector expressed in a reference frame which is not the one in which that derivative is computed, right? That's perfectly fine. So, but it is true that if I'm going with the particle, I don't see the particle accelerating, so I must see 0. So in other words, what is happening is that it's the acceleration of the particle times the mass and the forces acting on it. For my perspective, for me sitting here, they are canceling each other. So in other words, you can kind of look at this equation as, from me sitting on the particle, I only see this. I only see the 0 part of this equation. From someone outside, they see this. They see, oh yeah, that guy sees 0, but just because he's sitting with the particle. So he's feeling the force, but he's also feeling this, and they are canceling each other. Yeah. Okay. Any other questions? Wow. Short lecture. I don't want to start anything today other than this. Okay. Thanks.